Hello, it's Keith here, and this is lesson 45 of the platform-specific series of my 650 to Assembly programming tutorials, and we're going to be looking at the BBC, and we're going to be taking another look at sound. Now, if you remember quite a while back, we wrote a simple sound driver, which I referred to as the Chibi Sound driver. It was basically a way in which I could program all of the systems I cover in my tutorials and make sounds in a vaguely similar way using a single byte parameter. This allowed for low pitch and high pitch sounds, quiet and loud sounds, and it allowed for noise to be turned on and off, but it only used a single channel. It only allowed for a range of pitches from 0 to 63, and it didn't really allow for very much else. You couldn't match the tones, so sounds didn't sound the same on each system. They would just be low or high. They wouldn't be the same pitch, so there were a lot of limitations of that. And so at the time I'd sort of jokingly suggested that I could maybe make a more advanced version later on for music. However, this became less of a joke because essentially it was easier for me to write my own music software than it was to try and find one that was compatible with all the systems I covered. So that's what I've done. Now basically what I've done is I've created a new version of what I called Chibi Sound at the time, called Chibi Sound Pro. This is a more advanced version which allows for multiple channels, up to theoretically 128, although the hardware won't actually support that many. It allows for noise to be on or off again, so we can make sort of percussion instruments like cymbals or drums, and it allows for a wide range of pitches. This time it uses a 16-bit pitch setting. It also allows for a wider range of volumes. We use a full byte for volume now, and while the pitches aren't matched for the hardware, a low number will be a low pitch and a high number will be a high pitch. However, what the pitch, say 64,000, won't be the same on each system. What I'm then doing is I'm creating a lookup table of an octave which has the correct numbers that you can pass to the hardware to get the same pitched sound on each system. So we've now essentially created a simple driver that abstracts the hardware beneath it, and we can then use that in a common way across all of the systems in the Z80, 6502 and 68000 tutorials, and there's no reason this can't be ported to other systems as well. So that is what this so-called Chibi Sound Pro is going to do. The title Chibi Sound Pro is a joke. It's not really very professional. It's based on the Sound Blaster Pro, which so it's just a joke name. It's just to imply that it's better than the original Chibi Sound. Now, if you're watching this, maybe you're not interested in my music software. I can totally understand that, but it's a good example of how we can access a large amount of the hardware of the system. Now, today we are looking at the BBC, and the system basically is capable of 3 tone channels, 1 noise channel, and that noise channel can either have a total of just 2 bits configuring the tone, and that gives 3 different pitch options, or it can be linked to channel 2. Now, this causes us a bit of a problem with our hardware abstraction driver, because basically what this driver does is it simulates a lot of the functionality of the AY sound chip onto every other system. That is that it has at least 3 channels. Each of those channels is capable of tone or noise independently, and each of them has a volume setting. So now in the case of this system, the BBC, that's not really true. There's only 1 noise channel, and if we use that in its full frequency range, we lose tone channel 2 as well. And the point of the hardware abstraction layer is it just has to deal with that somehow. The calling software, the tracker software, does not care how the sound software deals with the problem. It just has to deal with it, and we'll be looking at that within the Chibi Sound driver today. Now, before we go any more into talking about it, let's actually hear what the Chibi Sound test code will allow us to do. Okay, so here is the test software. So if I just start this up today, here we go. So you can hear here we've got a tone, and then if I press left on the joystick, if the joystick actually works for me. I'm having a lot of trouble with my joystick today on this software. There we go. So as the number goes higher, you can hear the pitches going higher. As it goes lower, the pitch goes lower. And if I press the joystick fire button, there it is, you can hear the distortion is being turned on there. So that's essentially what we are doing now. We're also passing volume, but that's not actually being represented in this test software. The test software is used for me to configure the correct pitches. I use some pitch matching software to get the various notes in the octave and create the lookup table accordingly. And so what we're going to be doing today is we're going to be looking at the driver software. Now, as I say, that is just for testing the tones. What I then have is this Chibi Tracks test, which is being covered up by my oscilloscope there. And this is the Chibi Tracks software, which is the music player. So if I run this now, we will get one of my songs. So this is basically what the software is designed to allow you to do. Now this music was not coded for this system at all. It was written in the Windows software and it was tested on the Z80, the Amstrad CPC with an AY sound chip. But the point is that it really doesn't matter what hardware is running underneath, the software will, the driver will deal with the conversions required. So it should sound reasonably similar on all systems. That is the intent. Okay, so let's go back to the documentation here and let's just have a look at what, we won't need the Chibi scope again. So let's have a look at it. And basically what we're doing is we are passing 4 parameters, or 3 parameters in 4 bytes, and we're simulating the Z80 registers, so we're using 0-page entries. We've got a H, which is a combination of the channel number. That's the bottom 7 bits, which will mean a theoretical total of 127 channels. Now the tracker software by default will use 3, so we need to make sure we can cope with at least 3 or so, but it's very unlikely we would get past a value of 127, but in theory we could, and our software is going to cope with that in some way. Now the top bit of the H is the noise on or off bit, so if that's a 1, the noise is turned on. The L register is entirely the volume, so that goes from 0 to 255, although virtually no system supports that volume range, but it's perfectly possible that they could, so I'm using a 4 byte for that. And the pitch is specified by D and D, and that is all of the functionality that the Chibi Sound Pro driver provides. It doesn't provide any envelope support. The reason for that is that envelope support is not universal across all systems, so we don't have it. You know, we've sort of selected a minimal set of functionality that we need to play music, and we've written a driver to do that for us. Okay. Now, the sound chip that is used by the BBC works in the following way. Basically, we send a single byte to a single port, and the combination of bits in that byte define what is actually going to go on. And the basic template is that the bottom 4 bits are the data. The next bit is the type of data. The next 2 bits are the channel from 0 to 3, with the third channel being the noise channel. And the L, the top bit there, the L is the latch bit, because some parameters take 2 bits, and the second one would be a 0, then the first one would be a 1. So if we're going to send a tone, we will send 2 bytes. The first one, the latch bit, is a 1. We have 2 bits for our channel, then a 0 bit, and then 4 bits for the low part of the tone. Then the next byte would have the latch bit as a 0, and then there would be 6 bits for the high part of the tone, the pitch. And so that makes a total of 10 bits in total. Now we're passing 16, so we're going to have to skip a few, but that's perfectly common across all of the systems. As I say, we have created a template format for the data passed, and knowing that it's going to be downgraded in most cases. The volume as well, we would pass a top bit of 1, we would pass the type as 1, and we would pass the 2 bits of the channel and the 4 bits of the volume. And then the final option here would have the channel as 3, and then we have special options for the noise option. Now there are 2 bits that pass the noise option, and these can be 0, 1 or 2, which are the 3 basic frequencies. But if we pass a frequency of 3, then this actually then takes over channel 2, which was a tone channel, and it uses the frequency of channel 2 for the noise. Now the Chibi Sound Pro driver supports both options. Now if we just try out the original here, now this is using the tone channel 2 for the noise frequency. So you can hear those sort of distortion sounds, which are supposed to be sort of a drum and a cymbal. If we enable the simple noise option, it will stop using channel 2 for the frequency, leaving that more available for tones. However, we will get much poorer quality. Now the cymbal effect has basically been lost, because we don't have enough range of frequencies to give that definition. So we've got a choice. Basically, we can either have just 2 tone channels most of the time and have the good noise, or 3 tone channels and we don't have the good noise. Now the way I've programmed this sound, actually I always use the 3rd channel for the drum effects anyway, so I know from the music I've written that we're going to be better off actually using the more advanced and using that tone channel. But the reason I'm explaining that is we're going to see that in the code. Okay, so let's have a look at the Chibi Sound driver for the BBC. Now, the first thing you will notice is there is this Chibi Octave definition here, and this is a lookup table of various numeric values, and these are the match values for the correct frequencies here for the note types here, and we've got multiple octaves here. And so what we do when our music software works is we look up one or two of these values for the note we want to play. So if we wanted to look up the note C in the octave 3, we would effectively read in this value here. Now, if we wanted to do C sharp, we would add these two together, 9516 and A0A5, and then we'd halve them, getting a between value between the two. And pitch bending, we would select even fractions between that, and that's how we can get our notes. So basically, we've only got the pure tones here. If we need sharps and flats, we have to calculate them, and if we need even more definition of slight pitch bends, which we can do for wavy sound effects, then we can do that as well. But the lookup table is basically solving all the problems of matching pitches across multiple platforms. As I said before, the DE pitch that is passed to this software, the higher number will be a higher frequency, but we have no guarantee how high the frequency is or how low the frequency is, because that will entirely depend on how the underlying hardware responds to different ranges of values. They won't all have the same curve. Some might have a straight curve from low to high, some might have a different shape. So as I say, we're using the lookup table for matched values. That's how we're doing things. Okay, now, so how do we actually set things up? Well, the first thing we have, and we don't actually really need them so much on this one, is we have an initialization routine and an update routine which are disabled on this system. Now, the initialization would do any essential setup of the hardware. For example, on a digital system, this would be installing the wave files that are going to be used to create the sound effects, but on this system we don't need that. The other one is the update. Now, some systems like the ZX Spectrum, for example, with its beeper sound, won't make it a constant tone unless we actually regenerate that tone, and so that's what that would do on that system. But on this one we don't need it. What we do need, however, is we need a lookup table, and this lookup table is the mask of the bits to define the different channels. Now, this will set the two channel bits here in all of the parameters. However, you'll notice there's 4 parameters here and we've only got 3 channels. The reason for this is we could be passed any channel number from 0 to 127, and so by having a lookup table of 4 entries, we can take the bottom 2 bits of the channel number and we can map all of those sound channels to something that exists, even if it would degrade the sound if we were trying to play to 127 channels and we're having to map those to only 4. The final thing is we are defining some bytes of data for something called channel noise. Now, this is to resolve the problem that the calling software is expecting that all of the sound channels have a noise capability, whereas on this system only one channel has a noise capability. So when any of the channels passed with the noise bit enabled, a flag will be set in this, and then when those channels are used again with the noise bit disabled, the one noise channel will actually be switched off. So it's to track the noise bit being disabled on one of those channels. As I say, we're basically emulating a wave functionality in a sense there. So the first thing we're doing at the very start here is we are setting all of the bits of FE43. Now, FE43 is the port that selects the direction of the data bits of the port that we actually need to use to set the sound values. So we need to first set that port to make sure it's available for writing. What we're then going to do is we're going to check if the noise is set to on now. So we're checking the top bit of L to see if noise is enabled. Now, if it's not, what we're then going to do is we are going to get the channel mask for the setting, and we're going to store that in B. So we're going to set the 2 C bits in B so that we can configure all of the settings for our channel based on the channel we've been passed here. So we're masking the bottom 2 bits because we've only got 4 entries there, 0 to 3, and we're then getting a value from channel mask and storing it in B. And then what we're going to do next is we're going to check the matching bit in the channel noise table, which would also have 4 entries, and we're going to see if that is 0. Now, if it is, the noise was off before, and if it's still off, we're going to skip the next section. But if it was on and it is now off, then what we're going to do next is we're going to silence the noise channel, because, as I say, we need to disable the noise in this case. So what we're doing here is we are sending a byte here with all the bits as 1. That will essentially silence channel 3, the noise channel. Now, on this sound system, basically a volume of 15 is silent and a volume of 0 is loud, which is a bit odd to me, but that's the way it works. and we write all of our values to FE41 to actually set a sound value on the BBC. Now what we're doing next is we are storing a 0 in the noise table to disable the noise, because it was set to on and now we're telling the system that it's now been turned off. Okay, now if we want to actually turn the noise on, we're going to branch to here. Now what we're going to do is we are going to basically again get the entry in the noise table, and we're going to set it to 1 to set that channel's noise state to 1 so that we can know when to turn it off. If the conditional definition simple noise is enabled, then we are going to actually only have a frequency of possibly 2 bits, actually less because we only want a value of 0 to 2. So we're shifting those bits and we are effectively converting that to a value of 0 to 2. So that's what we're doing there. We're then ORing that in with the bit to actually set the frequency there. So we're setting the noise mode to 1, we're setting the channel to 3 here, and we are just setting the bottom 2 bits that are the rate here. So that's what we're doing there, and we're storing that into the sound setting there. Then what we're doing is we're getting the volume. We are EORing it because the volume byte that is passed in ZH will have the value 255 as the loudest. This one wants the value of 0 to be the loudest, and we are also setting the top bits so that we're setting the channel volume for the noise. And then once we've done that, we've actually finished if we're using simple noise. But if we're not, well, we've got some more work to do. So what we're doing here is we are setting the channel that we're going to set the frequency to channel 2, because if we set the rate to 3, the tone channel 2 will set the actual frequency. So we're going to send the frequency data to channel 2 here. And that's why we're setting B to channel 2 there. And then what we're doing here is we are muting channel 2 because we want channel 2 to set the frequency, but we don't want it to make a sound. So that's what we're doing there. And then what we're doing here is we are setting the noise and we are setting the rate to use channel 2 via the bottom 2 bits of channel 3 setting there. Okay. Now we now continue on, and we're now going to set the frequency. So again, we need to actually flip the frequency for this system. So we're EORing D and E here, and then we're shifting the bits because we basically need to shift our 16-bit value into a 6-bit value and a 4-bit value. So we're shifting the first part here, and we are then sending the low part, the bottom 4 bits. We're ORing in the channel number here, and we're sending that along. Now what we're doing then is we're getting the top byte, and we are taking the remaining 6 bits and we're sending those as well, because remember we send the tone frequency in 2 parts here. So that's what we're doing. Okay, now if we are not using simple noise though, what we now need to do is we now need to redirect the volume, because we are setting the tone of channel 2 here if we're not using simple noise. But if we aren't using simple noise, we need to set the volume to channel 3, the noise channel. So we are just double checking that there, and we are then setting the channel that we're going to change the volume of back to channel 3 here. We're then loading in our volume byte. We're shifting the bits to the right here so that we only have 4 bits. We are flipping the bits of the volume, the bottom 4 bits, and then we are setting the other 2 bits. We need the top bit to be 1, and we need bit 4 to be 1, and the 2 bits in between to be the channel. So we're ORing in the channel here, and then we're sending that to the hardware. So that is setting the volume correctly. And so there we go. So that is how we are creating our sound driver, and how we are basically taking these generic parameters and converting them for this hardware. Now, as I say, if you don't want to use my sound driver, you're of course welcome to not do so. Makes perfect sense. But maybe you can have a look at this and maybe you can understand how to configure the various parameters with regards to the noise and the volume and the tones. Hopefully this would make a nice simple example if you were just looking to do things yourself. Now this one is a little bit more complicated, of course. If you want to see something simpler, just check out the original Chibi Sound driver. That only had more simple functionality. But I'd say either way, hopefully this is interesting to you. Now, if you like what you've seen and if you're interested in this music software, please consider backing me on Patreon, because it's taken a lot of time to write the software. And it's not just the software that you've seen today. I've also written a Windows-based tracker, and it's taken a lot of time. It's been very difficult. So if you want to see that kind of content, please consider backing me. Anyway, I hope you've enjoyed what you've seen today. Go to the website, download the source code and the build script as always, and use them in any way you can. Thanks for watching today, and goodbye.